I'll also try to provide you with the basic understanding of econometrics and all. Uh, Throughout the process of this lecture series, initially I'll start with the theoretical understanding and underpinnings, and later we'll dwell into the applications and derivations of the important factors which are involved into the subject of econometrics. Rather than making it too mathematical or too technical, I'll try to make sure it makes sense for even the layperson. Uh, since econometrics is not just the subject which is highly relevant to the economics as a subject, but rather its application has been expanding, and many subjects which have an element of human interaction which can provide the randomness to the subject matter has the use of econometrics. And you can also see econometrics being used in the various uh, sister disciplines of humanities and social sciences like environmental economics, development economics, and all. So I would love to present some theoretical underpinnings of the econometrics so that it can better lay the foundation for the further study in the econometrics and all. Uh, to start with, econometrics, our traditional econometric methodology proceeds the following steps in order to dwell into conclusion, or in order to dwell into some sort of result at the end or object at the end. So it will start with the theory or hypothesis, which can be backed by any logic or backed by any commonsensical observation, and later we'll specify the mathematical model of that theory, and we'll try to have some statistical or econometric model which will be highly related to that hypothesis or theory, and also mathematical model which has been formulated in the before stage. And later we'll obtain data from the different sources, like we can find the real-time data which can be accessed through RBI data in case of India, and also we can find the stock prices rates from BSE website, and as well as you can find the international GDP rates and other economical macroeconomic variable rates from IMF, World Bank, and all. So you can obtain data from there, and later we can estimate the parameters of the econometric models through using such data and other techniques which will be dwelt later in this lecture series. Later we'll test the hypothesis whether that parameters which found in the earlier in the earlier steps are whether they are significant, statistically significant, and whether they make sense, whether they are to be considered as the true or near to true parameters. And later we'll use that hypothesis, and we'll use that results of hypothesis later in the forecasting and prediction. And this model at the end can be used for control or policy purposes. And in the whole econometrics, the term regression is heavily used, and econometrics, like regression is a subset of econometrics, but rather regression has very heavy synonymous attachment with econometry. So regression is the term which has been, or the concept has been introduced by the Francis Galton, where he observed that everything regress to the mediocrity. Now, like everything regress to the mean or average. So if you consider the like this is the example which has been quoted in the Gujarati, and that has been derived from various research papers which supported the argument of Francis Galton, which stated that if you observe the height of the tallest offsprings of the tallest parents, or and if you observe the heights of the uh, offsprings of the shortest parents, they will all tend to regress to the mediocrity, or may tend to regress to the average. And at the end, you will not find the world where there is only high height personalities and low height personalities, but rather you will find the average height of the population will regress to mediocrity or average. Even you have outliers. So this is not so regression or not regression is not just about mediocrity or average, but a modern interpretation of regression is, however, quite different. Broadly speaking, we can say regression is the concern, like is basically concerned with the study of how dependence of one, like study the dependence of one variable or dependent variable on one or more other explanatory variables, like so these can be, like these relation can be used further in prediction of the population mean or sampling mean, and from which we can derive population mean, and which can be used for the prediction and all. So if our aim is just for getting that mean, so we'll discuss that later in the part of lecture series. uh, there is a difference between statistical dependence and functional dependence. So in the whole econometrics and regression analysis, we consider the statistical dependence. So to understand better the statistical and functional dependence, we should basically distinguish between two subject matters of the world. there are primarily two subject matters which basically concerns the academic literature or some or anything per se. So there are two domains majorly: natural sciences and social sciences. So in natural sciences, the human element is very low or absent. In the social sciences, you have high interaction with humans. So if you consider a lab experiment where your blood has been put into test, so you will get accurately same results with the other blood, provided you will provide the same stimulus. But in case of humans, if you basically produce a same stimulus, you can get various other reactions from them. For example, if you slap the Gandhian, the reaction might be different. If you slap the person who follows the Hitler's ideology, the action can be different. So in this way, the reaction can be very different because of the human interaction. So in natural sciences, you can have the functional dependence or deterministic dependence, but you will not have such functional dependence in the social sciences, because you have randomness because of the presence of human element into that. So for that reason, we consider only statistical dependence in the econometric analysis. Then later, this regression. So regression basically consider the statistical dependence. So if you are doing regression and if you are able to find the statistical dependence between two variables, for example, if you say you are able to find the statistical relationship between consumption and income, so that doesn't mean you are established a causation. For example, income determines consumption and consumption determines income. Just because you are able to relate that to, like, because just because you are able to lineate the dependence between two variables, this doesn't mean that you are able to uh, imply causation unless until it has been backed by theoretical underpinnings. We are able to find that statistical dependence has some causation because it is being backed by theoretical underpinnings. For example, income and consumption is not, like, will not imply causation. Income doesn't imply causation of consumption unless until it is backed by the theoretical underpinnings. For example, you can consider the uh, Keynesian, Keynesian consumption function, where there is a really positive relationship between income and negative relationship with the interest rate. So that's how we should proceed. So statistical dependence will not, or regression will not imply causation unless it is backed by any theoretical understanding. So to consider this, Gujarati gives an interesting example. So in the reading called Gujarati, you will get an interesting observation where it states that if you consider, uh, like, you may find the statistical dependence between the crop yield and rainfall. So if there is, like, if you are able to find, for example, the statistical dependence between the crop yield and the rainfall, this doesn't mean that if you there is a causative relationship between crop yield and rainfall. You cannot say, like, for example, if there is a positive dependence between the crop yield and the rainfall, you cannot say just because crop yield has increased, you can expect more rainfall next season, right? So this is not how this causation proceeds, like statistical dependence proceeds, but rather they should be having standard theoretical underpinnings under to basically declare the causation. And there is also another related concept uh, in regards to in regards to statistics, that is correlation. So correlation is measured through simple formula, which basically states that summation of deviation from mean of two elements which has been taken into consideration by the variance of such uh, like standard deviation of such deviances. So such variables. You can find that formula in the internet. This correlation basically measures the degree of linear or strength of the linear association between the two variables, for example x and y. But this degree of linear association is not measured by the regression. Regression just considers whether there is a relation, like dependence between two, so that we can predict the future. But in correlation, you are finding the strength or degree of linear association between two variables. And there's also uh, a important distinction between the correlation and regression. Where basically in correlation, for example, if you take correlation between two variables x and y, that x and y is taken similarly. Like, you are not taken like, there is no asymmetry in way dependent and explanatory variable are treated. Like, for example, if you consider y is the dependent variable on x, which will be independent variable, these two will be considered on the same par, like they will be considered with the par. But if you consider like in the case of correlation, but if you consider regression, uh, you assume y to be random, which basically depends upon x. X is not random, so here x, which is the independent variable, is given. So basic assumption of regression is that x is given, x is fixed, and later y is predicted upon using x. So x is fixed, and later we will get to know y through x. So this is the basic fundamental difference between these two. And uh, in correlation, you basically assume that the two variables, that is x and y, are to be random. But in the case of regression, x is fixed, like that is independent variable is fixed, and y is assumed to be random or stochastic. So, so the term random or stochastic is heavily used in the econometric analysis. So, random or stochastic variable is a variable that can take any set of values, positive or negative, with a given probability. If you say a variable is not stochastic or not random, it's fixed, then you will not have the case of probability, because you have a 100% probability of that variable, because that is fixed, that is anyway will come. But if you attach probability values to any variable, you are attaching an element of randomness. So it can, like, you're just saying probability, you're not saying with the fixed intuition or uh, like you can't fix upon some decision unless until such thing, like in probability you are just like attaching values of probability, like there will be probable event x, but you're not saying surely it will happen. So if you are saying it surely, then it is not stochastic or not random. But you are attaching, but if you are attaching probability to that value, then you are creating a sense of randomness into that. So that's the basic analysis. And later there is also very different types of data which has been used in the econometrics analysis. So uh, in the initial few lectures, we'll consider the operations on cross section, and then later we dwell into the time series. So first, to consider the time series data. Time series data, basically in time series you basically consider the data across the time periods. For example, you may take the data on consumption from 1992 to 2022. So these data is called as time series data. So in time series data, we assume the assumption of stationarity. So stationarity is nothing but where you assume that mean and variance will not vary across the time period. So these are the basic assumption behind the time series analysis. But these time series analysis, like stationary and all this technical meaning attached to it, will be dwelt after chapter 20 of Gujarati. And if you consider the cross-sectional data basically takes into consideration various variables collected at the same point of time. So in time series, you basically varying the time. In cross-section, you are varying the variables. Okay, in cross-section, you will have variables like consumption, income. You may also have variables like taste and preferences and all. So you considering various types of, like, various variables of data. And in pool data is another type of data. So in pool data you consider, so in pool data, in the next category we'll have pool data. Pool data is nothing but a combination of time series and cross-sectional data, where you consider the different variables across different time zones. So you may consider the consumption, income, and tastes and preferences across different time zones like 1992, 2022, and all. And the panel and longitudinal or micro panel data is the subset or the some sort of special type of pool data, where you consider only a particular unit, only a particular cross-sectional unit across the time zone. So that, for example, if you're considering only set of families, like 10 families in a place or in a village, and you will observe that 10 families uh, like behavior, like consumption behavior, for example, across a time data, like, so like across a time series, so that you will have a understanding like how dynamics of household behavior is changing across the time zones, like across the time. So for that you will use the panel, longitudinal or micro panel data. So that's in regards to data types. And there is also an element of, like, in panel also you'll have a balanced panel and unbalanced panel. In balanced panel you will take uh, across all cross-sectional units, like for example we consider the families. So across all families you take same number of observations. If you are not taking same number of observations or units, then it may be called as unbalanced panel. And there is also another category of data, for example, experimental and non-experimental data. These experimental data is a data where individual can control the consequences and stimulus, which is very possible in the natural sciences as we discussed earlier. For example, laboratory experiments. In non-experimental data, we don't have, like, investigator cannot control. Okay, so that's basically the chunk of social sciences experiments. And there is also an important concept attached to the econometrics and data analysis, that is measurement scales of variables. A ratio scale, if a variable can be represented in x1 by x2 form, then it can be regarded as ratio form. And if you having two values, for example 100 and 200, like 200 kilometers and 100 kilometers, and the distance between them, like two of that variables x1 and x2, makes meaning. And even you can arrange that in the natural ordering. For example, 200 kilometers is greater than 100 kilometers. So these two characteristics are very inherent to ratio scales. That is, you can represent in the p by q form, and you can also represent through distance, and you can, and they have natural ordering, and these natural ordering are meaningful. And most of the economic variables, interestingly, belong to this category. And there is another category called interval scale, where you measure between two time periods. For example, say 2020 to 1990, or 1990 to 2020. And so the difference between these two time zones are meaningful, but you can't uh, essentially attach meaning to the ratio. What's ratio, like, what will be meaning if you divide 2020 by 1990? Of course, there is no meaning, right? And so that's the thing. And you can also uh, there is also another scale called ordinal scale, where you basically, like, you may consider the grades like A, B, C, or you can consider the hierarchy in the society: upper class, middle class, and lower class. And this category has only will only satisfy the property of natural ordering of ratio scale. For example, you can grade A is greater than B is greater than C. You can't like, there is no meaning of difference, and there is no meaning of ratio here, right? You can't divide A by B and find out some meaning, and you can't simply subtract A minus B. What will be the result of A minus B? Nothing. So that's the ordinal scale. And in nominal scale, you basically consider the variables such as gender, marital status, where there is nothing mean, like, the features of ratio scale will not apply here. You can't basically attach meaning for subtraction of male minus female, and male by female has definitely no meaning. And you can't also order in the natural ordering, like male is greater than female or female is greater than male. There is nothing meaning attached to that. And so after this, we essentially dwell into the concept of regression even more deeper. So in the first concept of regression comes with the PRF, that is population regression function, or population regression curve, or this population regression curve basically is the locus of the conditional means of dependent variables for the fixed explanatory variables. Like, the basic essence of regression comes with the fixed variable of explanatory variable. So you fix some explanatory variable. For example, if you consider income as the explanatory variable for consumption, you will essentially fix that income, and then you will consider the mean of that income level, and you will draw a line passing through different income levels. Like, if you fix income level at 100, you will have average for that 100 income level, and again you will fix for fixed income at 120, and you will have average for that 120 income group. And when you draw a line which is passing through the mean of these various income groups, then that line is known as PRF, and this can be geometrically represented as this. So essentially, this is the PRF, and these are the conditional means. The circles and circle is the conditional means. So you are fixed income at 80 first, then later 140 and 120, and you will have data spread across these conditional means. Uh, and these dots, like circles, represent the conditional mean. Conditional mean is nothing but you are attaching condition, that is income is fixed. So if you are not having condition attached, if you have unconditional means, then you will basically sum all the observations and you divide for simple average or mean. So that's the difference between conditional and unconditional mean. Uh, Essentially, this PRF is the function of uh, xi, that is independent variable. And later we can also determine how xi is determined through this equation, that is beta 1 and beta 2 into xi. And this beta 1 is the stochastic, which is intercept, uh, and this is determined through the interaction with xi. And this beta 1 is basically intercept variable, and this beta 2 is the dependent on the xi, that is fixed income, if you consider this as the consumption. uh, so that's the case of PRF, and using these PRF you basically so there is also stochastic element attached to PRF. So if you consider this conditional mean, so PRF lies here, but true value can be above PRF or below PRF. So if it is above PRF, then you have some element of randomness, and even if it is below PRF, then you have some element of randomness. And these randomness are common in this statistical dependence, as we discussed, because it involves the human behavior. So if the variable has randomness, then the PRF functional form takes this form. So you basically attach the value of uh, what randomness to it. Like this UI represent the stochastic element, and this EYXY represent the systematic or deterministic component. So that's so if we can decrease this, like this UI can be also representative of the elements which we are not taken in the functional form. For example, consumption can be dependent upon various other variables like tastes and preferences, like geographical location, and the political stability at that point of time. For example, if there is war, then you basically save more for the later as a preventive measure, okay, precautionary measure, which is the word used by the Keynesian analysis. So these randomness can be decreased by using more elements, uh, but it is basically commonsensical to argue to decrease this to 0. But is it possible to decrease that to 0, and why it cannot be eliminated? Like why not include more variable to eliminate UI, that is randomness? Why can't we include more variables such that total stochastic element can be removed? Total that randomness can be removed. There can be 6-7 reasons for that. The first one is the vagueness of theory. So if you include more variables, there will be vagueness of theory, and there will be no proper theory which mentions that everything, like you can't establish a theory which basically includes every other factors which influence the consumption, for example, right? And there is also issue of the availability of data. You can't get data for everything, and core variable, like you can't consider peripheral variables which can basically have very low influence upon the dependent variable. You can't consider, like if you are able to find out income has around 80% of the relation, like 80%, like income can explain 80% of the fluctuations in consumption, then why to consider the other variables which are just representing 20%, right? And there is also intrinsic randomness in human behavior. Even if you include all of the factors which influence consumption, there will be an element of human behavior which can basically deviate from that estimated value. And there is also issue of poor proxy variable. If you consider the Milton Friedman's permanent income hypothesis, where he considers the permanent, like consumption is the function of permanent income. So here you can't estimate permanent income. Permanent income is the income of the future. So how can you take proxy for that? That proxy, Milton Friedman took proxy as consumption, like per capita income in case of in case for permanent income, and consumption expenditure for the permanent consumption. But this is not accurate. Like you can't accurately measure the permanent income and permanent consumption using these variables. So there will be issue of poor proxy variables. And there is also principle of parsimony. For example, if you are able to estimate uh, a particular thing using very least amount of uh, variables, then why can't you bother to include more variables to make it more clumsy? So this is and there is also another issue of functional form, wrong functional form. Like who will know the functional form? Like if you are able to define a functional form of the two variables through graphical representation, it's fine, but how many data points you should take to basically determine that graphical representation? And even what if the graphical representation is inconclusive? How can you determine the functional relationship between consumption and geographical location? How, whether it is positive or negative? So that's very interesting to note that it's not possible to eliminate UI or randomness altogether, but rather we should make sure efforts to decrease UI. So that's what this lecture basically deals with. And in the next lecture, we will deal with the SRF and how SRF can be used to estimate PRF. Thereby, after that, we can basically After that we basically dwell into OLS method, or ordinary least square method, where we'll be minimizing this UI so that we will get better estimation of uh, like we can get better estimator through which we can estimate PRF, and then later we can use that parameters to accurately measure and predict the future values of dependent variables using the fixed independent variable. So that's all for the today's lecture. Thank you.